Yeah, everything's good. Can everybody please find a seat? Some people coming. Okay, it's a pleasure to welcome you here today and the Department of Physics for Professor Will Branford's inaugural lecture. As I said, I wasn't sure whether we were allowed to call you professor before or is it only after, but I think yes. So for Professor Branford's inaugural lecture, the order of things, first we'll have Professor Sapienza, who is the Deputy Head for Research in the department, introduce Professor Branford. We'll then have the lecture, then we'll have a vote of thanks, and then there will be some drinks outside to celebrate the occasion. So please.
I think
you are.
Yeah. Thank you very much. Welcome, everyone. Before I start, some housekeeping. There's no fire alarm test planned. So if you hear an alarm, please follow the route. We will exit the building, and the assembly point is in Queen's Gate with Princess Court of Consort Road. There will be a recording of this lecture, and at the end, there will be some chances for questions, both for people here and people online. And it's my pleasure to welcome you to Will's inaugural lecture. This lecture celebrates the career and achievement of our colleagues, and Will in this case, and there's a lot. And I will not spend much time saying that. Just a few minutes to go over the career of Will. So Will joined us in 2002 as a postdoc after a PhD in the Royal Institution. We'll probably hear more about that later. And in 2012, became lecturer in physics, and now is professor of solid-state physics. So Will research is in the field of magnetism. Is a world expert of spin ices, and in particular, he defines and studies magnetic fields that he creates using structures. This is a really interesting area of research, which has many fundamental applications, but also is very applied or can be applied. And Will, in the last few years, has applied that to a new form of computation as a hardware for a new kind of computer. And I hope you will tell us about that. It's great to have Will as a colleague. It's really a privilege to work alongside him as a wonderful colleague, and he has done more to our department than just research and teaching. And he has supported us in multiple ways. He has been, since 2003, head of the Matter community, leading a large group of academics. And recently is the co-director of the School of Convergent Science in Human and Artificial Intelligence, which is about to start, or starting, which is across the full college. So this is another great achievement. So I really don't want to spend more time. They don't want to hear me, but Will. So please welcome Will to his lecture. Thank you very much.
Thank you very much, Riccardo. Okay. So firstly, I'm Will. You're welcome to call me Will. And thank you all for coming to hear what I have to say today. So this place means a lot to me, and this is a really special day. And I'm delighted to share it with so many friends and also my family. Quick shout out to my daughter Matilda, who can't be here because she's on a school trip to Spain. But anyway, let's get into it. Okay, so my title, rather ambitiously, is How Physics Made AI Possible and How It Can Make It More Efficient. Okay, so what does that mean? So, oh, we've got more of these. Okay, here we go. Right, okay, so the first bit, if you like, is an origin story. It's not really my research, but it's the inspiration for my research. And so really that's about how doing curiosity-driven research led to statistical models of magnetism and emergent network behavior. And these really powered and inspired the early artificial neural networks. So having introduced that, I'll show you my work, where to start with, we use nanomagnetic arrays as a kind of tractable, controllable, and also imageable host for the sort of physics that powers AI. And I'll give you some examples of that very briefly. And then after that, I'll kind of give you an introduction to, if you like, the dark side of AI, which is how much energy it uses to do the things that we rely on. And so having introduced that, I'll show you a little bit of our recent work where we're really trying to do the sort of computing which is, if you like, brain-shaped or neuromorphic. Well, it really is, the idea is it's specifically designed to do machine learning rather than traditional computation. So I'll show you very briefly some of the computing we've done so far, where we use an input of magnetic field, which is, it's impressive as far as it goes, but that's not really a commercial technology. So what we want to do is get a better input scheme. So the last thing I'll show you is a lot of work that's going on at the moment, where we're trying to replace that with optical input schemes. Okay, and then finally I'll wrap up with and how can it make it more efficient bit, and I'll give you a bit of an outlook and future plans. Right, okay, so our story, like all good stories, starts with magnets. And basically, just so we're all on the same page, if you have an electron, it has a spin as well as a magnetic charge. And so you can have some cartoon here like this. Here's our electron. And the spin is basically a sense of rotation. So the magnitude of the spin is always half, but it can be plus or minus. And then for a spin half single electron, if it's going around a hydrogen atom, then the magnetic moment that you get from that single spin is exactly 1 Bohr magneton, which is our fundamental unit of magnetic moment. But if you have a helium atom with 2 spins in it, then they have the opposite sense of rotation, and so the total spin is 0. So that cancels out. And in fact, that's true for any full orbital. And if you remember back to your chemistry lessons, then the sort of stuff that happens over here in the left wing and the right wing, basically, as we go across those bits, we're filling up the s and p orbitals, and those are where the bonding electrons live. And the first rule of bonding is basically you try and get rid of any unpaired electrons. So these are not promising for magnetism at all. Whereas when we go across the transition metals, these things in the middle here, and also the lanthanides down here, those d and f orbitals do not contribute to bonding at all. And so there you can have very many unpaired electrons very stably. And so this is a much more promising area for magnetism. And so the colored elements are the elements that are themselves magnetic, just as the pure element form. But most of those atoms or elements in the middle are promising materials to have magnetic atoms. Okay, so rather than draw it all out, I've got this lovely video which was made by Parasekle, so thanks to them. And basically, so if we have an atom with unpaired electrons, then it's got a total spin, and this controls its moment. And then basically that's sort of free to rotate like a little compass needle. Then if that's in a solid with very many electrons, very many magnetic moments, then they form an ensemble. And so they move freely with the thermal energy. But when we put a field on, you can see there's a tendency for them to all align in one direction. And so basically we suppress the thermal motion completely by putting this field on. But then if we take that field off again, then basically it will just go back to how it was before. The thermal motion will come back. And this is what we call a paramagnet. And at this point, we're assuming the magnetic moments are not interacting at all. But as I'm sure you could figure out, if you put 2 magnets that close to each other, it's very likely they will interact. So here we've got a ferromagnetic interaction. And so what that means is that the 2 spins have a tendency to align in parallel to each other. And so you can see that they're still moving around, but now they're in lockstep with each other, right? Because they want to be parallel to each other. And then if we start thinking about that on a much bigger ensemble, so to start off with it, we're imagining it's very hot. So everything, if you heat it up hot enough, the thermal energy will win. And so these things are thermally fluctuating, but you can kind of see there are correlations between neighbors, so it's not totally random anymore. And then if we then cool down from that situation, what you see is to start with the thermal excitations get weaker and weaker, and the alignment gets better and better. Then at a specific critical temperature, suddenly all that stops and it goes through a phase transition. And at that point, everything is perfectly ordered. Okay, so you can see the movement decreases a bit more as you go even colder, but broadly that's the point where we no longer have random order. We've got one particular form of magnetic order. Again, one last thing I want to show you on the video, which is going to be important later on, is if we now imagine this ferromagnet. So everything has an average magnetization direction, which is perfectly ordered. But if you either warm it up or excite it in some way, you get what we call spin waves forming. So this is precession around the average magnetization direction. And so essentially, these things are coupled, and so the spin waves can then flow through the material. And these have a very characteristic resonance, which is really sensitive to the exact total magnetic field that's being experienced. So essentially, this is an incredibly sensitive probe of the total field strength in the area. Okay, so there we are. Okay, so anyway, so what are our magnetic interactions? Okay, so if we're in atomic spins in a material, then almost always it's the exchange interaction which just dominates, and this is our equation here. And broadly, the dot product between the two S's governs the angle between the two things. And basically, this is a quantum mechanical effect, and it requires the overlap of the orbitals. And because of that, the J constant out the front here is a really sensitive function of both the geometry and the distance and the angle and things like that. And so while we always expect that at some critical temperature we should get order when our interactions are stronger than the thermal energy, in fact, what we see is that in some materials you never see this order. You always have motion right down to very low temperatures, and the reason for this is what we call magnetic frustration, where basically not all the interactions are doing the same thing. You have competing demands. And the archetypal material for this was the spin glass. And so why was there no order in the spin glass? Well, so Sherrington and Kirkpatrick were very interested in this. And so even though the materials weren't obviously useful, they generated some solvable model, and they're able to get some traction with the problem. And then shortly after that, Parisi produced an exact solution in the thermodynamic limit. And one thing to say is that the spins can have different degrees of freedom. What I showed you before, they're kind of free to move in all 3 dimensions, which we call Heisenberg spins. So sometimes the spins are only free to move in 2 dimensions, which we call XY, or just in a single dimension, which we'll call an Ising spin. Okay, and so basically when you reduce this dimensionality of the spins, all sorts of other interesting but similar forms of statistical physics start to emerge. So this is the 2DXY model, which has a vortex phase. And so the properties are governed by these emergent vortices and anti-vortices. And in a spin ice, it's a 3D structure, but the spins are only have degree of freedom in one particular direction. And so I'm very pleased that Steve Bramwell is here. He was my PhD supervisor. And so really, he showed that here you have a kind of local ordering principle, but again, no range order in this structure. Right, okay. So at this point, I wanted to have a bit of a Socratic dialogue, and rather than just talking to myself, I made a hero and a cartoon strip. And in the context of this talk, and also in the context of my artistic skills, what this meant is that I got my generative AI of choice, and I asked it to have a scientist saying the following things to me. So, hey, Will, I'm sure all this statistical physics is interesting to you, but Imperial's founding charter is to be useful. To change it, you need an act of parliament. So basically, you have to be useful. It's the law. And so it's a fair question, are these things really going to be useful? But one thing you might notice is the speech bubbles look a bit funky. So while kudos to Copilot for the beautifully diverse workplace it's generated, I was a bit less impressed with the speech bubbles, because this is what it actually did. And so it's a bit of an uncanny valley situation where you interact with an AI and it's brilliant at text and it's brilliant at pictures, but you ask it to put pictures on the text, then because the two things are so different, it becomes kind of hopeless. And so you can see there's bits where it's just like nonsense words that it's hallucinating, and there's bits where the letters are kind of merged together by the diffusion model in a way that DALL-E would have been very proud. And when I say DALL-E, I mean the artist, not the AI model. Okay. So anyway, coming back to is it useful or not? Well, basically, so from this model of Sherrington Kirkpatrick, then very soon after that, basically Hopfield was able to use this model to build what we call the Hopfield network, which was the first ever artificial neural network. And so really, on this picture here, these sigmas are the spin states, and these lines, or the weights, really are the magnetic interactions between one bit and the next. And basically, Hopfield showed that you can do really nice machine learning in this system. Now, if you generalize that machine learning model a little bit, you can get what's called a Boltzmann machine, or there's a similar thing called an Ising machine as well. And to put it another way, if you kind of generalize any of these structures where you've got like an ensemble of things moving with energies and temperatures, we describe those with a Boltzmann distribution, and so we can generalize to these energy-based models. And whether it's useful or not is one thing, but it was certainly interesting. So Kosterlitz and Thulis got the Nobel Prize in 2016 for topological phases, transitions and phases of matter. Parisi got the Nobel Prize in 2021 for the interplay of disorder and fluctuations in physical systems. And then this last year, Hopfield and Hinton got the Nobel Prize for foundational discoveries and inventions that enabled machine learning with artificial neural networks. So really the thing I want you to take away from this is because Sherrington and Kirkpatrick were curious and did something, to try to fundamentally understand some interesting materials, the consequences were totally different, but they basically changed the world, as we know it today with all the development of AI. Okay, so next, how do I fit in? Okay. So anyway, at this point, we're going to go to about 2006. I've done my PhD with Steve, and currently I'm working as an RA with Leslie Cohen. He's our next key feature. And so basically at that time, Peter Schiffer's group showed that if you make an array of nanomagnets, then each one of those nanomagnets will act like a gigantic or macro spin, and also that you can arrange them in patterns where we can get these whole same arrangements of frustrated magnets, so you're able to realize all the physics that we know and love. And I thought immediately, sign me up. And as I should say that I was Leslie's postdoc at this time, and this choice of project might not have been Leslie's first choice, but she was hugely supportive, and I'm very grateful for the opportunity she gave me to get the proof of principle results, which turned into my first big fellowship, which was called Defects in Frustrated Systems. But as well as looking at the fundamental physics that powers AI, really from the start, I thought, well, this kind of looks like a Hopfield network, but rather than simulating it on an ordinary computer, we can really have spins and interactions in the hardware. Okay, so we need some building blocks to do that, and our building blocks are these nanomagnets. And if you have a big lump of iron, it is a ferromagnet, so on the scale of atoms, it looks how I showed you, all perfectly lined up. But on the scale of micrometers, it breaks up into what we call domains. So the average magnetization is 0. And so something made of iron won't usually stick to your fridge, for example. But anyway, so what we see is that also if we shape it, so it's kind of long and thin, then because you want the poles to be small, it will magnetize along the long axis. So we've got the Ising spins that are characteristic of spin ice. And also we have these magnetic charges. So this is just the poles, but it's helpful for bookkeeping to actually call it a plus or minus charge rather than just a north or south pole. Okay, and then if we arrange them on the lattices we know are great, so like there's a triangular arrangement here, then the first thing to say is that you've got 3 magnets meeting. One wants to have its north pole in, the other one has its south pole in, so they're both happy. But then the third one is going to be equally unhappy whether the north or south pole points in. So what that means is that over these 3 things, you finish up with 6 different states, which all have the exact same energy as each other. So it doesn't know what the right answer should be. And then, so looking ahead, the big controversy or excitement in spin ice at that time was the prediction of Claudio Castelnuovo, that basically the kind of physics of spin ice could be much better described and solve a lot of problems in the field if you had what's called a magnetic monopole model. And so this picture is essentially a freeze frame by definition. And so where you have these like balls of positive and negative charge, or similarly, in my structures, that would be 3 magnets pointing in on the inside and all that. So it's like, it looks the same in terms of the charge from all directions, but much more importantly, the kind of dynamics of the thing were such that all the magnetic fluctuations and reversal were governed by the formation and then the motion of these defects. So making one of these excitations costs you a lot of energy, but then once you form them, they can basically hop from site to site at no further energy cost. So essentially, these then form quasi-particles which control all the magnetic properties, and that's totally different to how most magnets behave. Okay, so shortly after that, various groups shown here. Steve was a very important figure in that, showed it with a lot of experiments that this was really the case, and what we now call the Coulomb phase came into being. But basically at the same time, we were trying to take a picture of these things in artificial spin ice. And here's, if you like, the freeze frame of the defect. So you're going to see quite a few of these, so we'll spend a little time explaining. So basically what we're doing is called a magnetic force microscope. And so basically we have a scanning probe tip, which is a little like North Pole, and it scans over the top. And then the phase that we measure is governed to the strength of the charge, the magnetic charge underneath it. And so as we go over most of the sites, you can see we get this phase contrast of about 1/3 of a degree. There's a minus, there's a plus, there's another minus. But then there's this one site here where we get 3 times as much phase, and that shows that the charge is 3 times stronger. So this is our monopole defect. And then perhaps much more importantly, because of the nature of the kind of the ferromagnetic artificial spinite structure, we can basically form a series of stop motion images. So we can keep taking a load of these things in sequence after a different field each time. And we can basically track these monopoles going through. And so the important thing is it's characterized as a ball of pure magnetic charge where the change is basically 2 in these units of Q. So because every vertex is always charged, then when it has a Q of 3, that's on a site which is normally a Q of 1. But sometimes as we follow the defects through, and here's the cartoon showing where they're going, the site is naturally a -1 site, and then it is +1. So the nature of the thing in the static changes, but the kind of conserved particle going through, which you could call a magnetic current if you wanted, is the same. Okay, so we showed that this is a really good vehicle, if you like, for these things. One thing I should say on monopoles before I move on, you may have heard of monopoles before, and basically that comes from Dirac, who made a theoretical observation, if you like, that if magnetic monopoles exist in the universe, then all electric charge must be quantized. And we know that all electric charge is quantized, that's quantum mechanics. And so he postulated this elementary particle. It's essentially the magnetic equivalent of an electron, and it's a monopole in the B field. And it's extremely important in cosmological theories of the early universe, such as the Kibble-Zurich equation. And as we were on the topic of people who should have got Nobel Prizes and didn't, I thought I'd show a picture of Tom Kibble, local legend and founder of this thing, lecturing in this very room. And anyway, so if these things do exist, we would have to rewrite Maxwell's equations. But, well, we haven't found any yet. So as far as we're concerned, Maxwell's equations are fine as they are. And so the one of Maxwell's equations that is called the no monopoles law says that you can't have any divergence in the B field. Okay, but there are also magnetic fields which we call the H field, which is the applied field strength and the magnetization. So the B field is the density of the flux lines. Okay, so in the other in the other magnetic fields, it's very common that we see monopoles in all sorts of different fields. So here's like hard disk technology, here's the kind of MFM field profile, this is band structure theory in momentum space. And basically, in all of these things, and in all the spin ice work, you can get magnetic monopoles, but they're always made up of magnetic dipoles in some way. And so unlike this postulated elementary particle, there's no problem with Maxwell's equations. But it's caused a lot of confusion that we say we found one thing and people think we found a different thing. And my view on this is that this postulated elementary particle, which people have been looking for 100 years now, really needs a proper name. And I'd like to humbly suggest the Kiblon in honor of the great man. Right, okay, so the next thing that was caused quite a stir in the kind of statistical physics of these lattices community was the idea that when you have the particular lattice we've got, which we call the Kagame spin ice, if you've got true vector dipoles, you wouldn't get any order at any temperature, but essentially when you have a finite length, it's subtly different, and you actually get all these complicated phase transitions. And these ICE1 and ICE2 things, they're very much like sort of the Kostler-Stulitz thing, which is very interesting. And in particular, this long-range order thing had a lot of interest, but no one had ever managed to find it. And so we were certainly interested in looking at the kind of transport properties of our structures as a function of temperature and seeing what we could see. And so we did some very careful measurements. And 100K, which was basically the same as room temperature, except a bit sharper. The important thing to note about like all of these things with the current, voltage, and field in different geometries is that they basically have a twofold symmetry about the 0 point. Whereas when we cool down to low temperature, the symmetry is broken, and you can kind of see the left half looks totally different to the right half in all of these structures. And so what's going on is rather complicated, but certainly we saw symmetry breaking transitions. And one thing that's important to note is that, because we have ferromagnets, we're not really in thermodynamic equilibrium. So what a phase transition would mean is not an easy question. But anyway, so moving on a few years, we're up to 2018 now. Still no one had found this particular ground state, but in the PhD work of Jack Gartside, he developed a lithographic magnetic force microscopy technique to actually write the magnetic spins rather than just image them. And so basically by doing that, what he's done now is he's prepared a particular state using a field to saturate in one direction, and then he's swept the tip across each wire he wants to switch in the opposite direction. So all the ones that are blue, he switched, and then we're able to get the exact state that we wanted and people have been searching for many years. Now, you might think that's fascinating topological physics, or you might think you cheated, you just wrote it. But whichever it is, what we showed is that we can write any pattern that we want, and we did it to write this particular one lots of people were interested in. And so really that's the point we started to think, okay, now we've really got a way that if we had like a hot field network type thing, we could really set the starting condition to be anything that we want. We can really control what's going on. Okay, so that was kind of the start of where we started seriously thinking about computing. And so let's think about AI. So I'm sure I don't need to tell you all the good stuff that AI gives us, like image recognition, speech recognition, efficient search engines, self-driving cars, all the rest of it. But all of this functionality, it needs, so it's achieved by doing computer algorithms that are mimicking these things with really complex networks. So many, many nodes now in the latest things, with an almost infinitely large number of pathways, and every single pathway has to be fine-tuned or trained over and over again as you go around. And it works spectacularly well, but it uses a brutal amount of energy. Okay, so here's a robot hand solving a Rubik's Cube, which is cool, but it took the equivalent of 3 nuclear power points operating for an hour to provide the energy to train that particular thing. Okay, and even a humble Google search, then 7 Google searches cost the same energy as boiling a liter of water. Okay, so these things really cost energy. We don't really see the energy cost of stuff in the cloud, but it's really there, and it's really important. And the particularly brutal thing with machine learning is as we're getting better and better at it, and these models get bigger and bigger, essentially the cost of training one of these networks is doubling every 3 months. So this is the region here. So basically ever since 2012, that's been the case. And this has really serious implications in terms of the CO2 emissions. So down here on this graph, this is generally considered to be one of the most carbon costly things, which is like a cross-continent plane flight. It's kind of like one in these units. And the cost of training ChatGPT-3, which is quite a relatively old model now, was already like 500 times as much as that. And if you assume that ChatGPT-4 or Google's Gemini were trained a couple of years later and it's doubling every 3 months, that means that the bar for those ones which are not available yet will be 256 times as high as that one. Okay, so the carbon cost is enormous and the energy cost is enormous. Okay, so this is some relatively like middle of the road conservative predictions of how much energy we're going to use on computing. And this y-axis here is like total global energy production. Okay, and this is how it's predicted to go in the not too distant future. And it's divided up. So you can actually see that the consumer devices and the production of the things is actually going down. But what's going through the roof are the data centers and the networks where we do machine learning. Okay, so this is a major challenge for us, and we're going to have to try and do something about it. And the root cause of this problem is the way we do conventional computing. So basically, we have 2 separate things. We have a logic processor and we have a memory, and they're separate devices. And even in ordinary computing these days, nearly all the energy is actually used in shuttling information between those 2 things, rather than either doing the processing or the memory. But this is particularly bad for complex neural networks. If you imagine you've got some giant network with 1 billion nodes, and like within a layer, they're all connected. That's 1 billion squared network weights that you have to store. And basically, when you're running the computation, any particular computation that you do is actually quite simple for the processor, but you have to store all those trillion weights while you're doing it the whole time, and it keeps having to call back. So it's just not suited to our current architecture in any way. And the idea that we could maybe do what's called in-memory computing, so actually do some fairly simple computing operations in the memory itself, is hugely attractive for this. Okay, so one last thing on this. There's a very cool thing from Riken in Japan, which is called the K-computer. And they tried to mimic the wiring diagram, if you like, or make a human brain out of conventional electronic components. And actually, they only managed 1% of like brain size. And still, that already used 13 megawatts of power to run. And it was 1,500 times slower than a brain. So overall, it was 10 billion times less energy efficient than our brains. So the great news is, biology shows us there's a way we can do much, much better than we're doing right now in terms of the energy cost of computing. Okay, so what have we done? How are we trying to do it? Okay, so one thing to say, I showed you these already. These are our nanomagnets, but we're going to add one more element into the mix to start with, which we found really helps our computing a lot. And that's to allow our nanomagnets to also form a vortex state. And so basically, that gives us a lot more degrees of freedom. So now, as well as the 2 macrospins, we've got 4 possible vortex configurations. So all of these things are stable, or at least meta-stable, so that they could last for hundreds of years if you don't put a field on. And so when we do that, the next vital thing is that we're able to measure exactly what's going on in our structures. And so really the key to this was the spectral fingerprint method of ferromagnetic resonance, which was developed in Alex Vanstone's PhD. And all the underpinning methods that were key came from the PhDs of Dana Roux and Troy Dion. Okay, so basically, so when we do that in our structures, so we get a spectrum that looks like this. But basically what we've done is we've done the same thing over and over again on these structures. So this is like the number of training loops, but each training loop is exactly the same as the one before. So we start with all of these fatter bars in the macrospin state. We put a big field on to saturate them. So we've got a huge peak. This is the macrospin peak. And these are actually the narrow bars. This is another macrospin peak here. But then as we cycled, just doing the same thing over and over, what we saw is that the height of this macrospin peak goes down and down and down. At the same time, this other peak here goes up and up. And this is the vortices forming. And so you can see that gradually one shrinks and the other grows over 30 cycles. And so the thing that's really nice about that is if you do something on a computer and do the same thing over and over again, you get the same answer over and over again. Whereas that's not what we're getting here. We're getting this kind of decay. And what it's much more like is how our brains work. You know, if you try and do the same task over and over again, then hopefully you get better and better at it. So here the task is like making vortices, but we've got a very brain-like property. And one more thing that's very important if we're going to think about computing is what the memory capacity looks like. So this is a very similar experiment. But here what we've done instead is like before the experiment starts, we've done the training to different numbers of loops. So we've got all these different states. So this one with a really high macrospin peak is kind of the starting point. This one down here is like basically everything's a vortex, and these are intermediate states. And then we give the system a kick to try and favor macrospin somewhat, but you can see the order stays the same. And then we go back to the same training as before. So again, we do the same thing over and over again. And not only can you see it's still going down as before, so we've got the kind of the learning property, but also you can see the order that these things in stays the same. So even like, you know, about 4 or 5 loops in, you can kind of see that we still know which is which. So we can go from this measurement to know where our starting state was. So that means we've got a memory capacity which is good, but also the more cycles you do, the weaker it gets, it gradually fades away. And so for the sort of the computing that we want, that's exactly the property that we want. Okay, so to show you in a bit more detail what we're doing, so our input, if you like, is one number, and here we're putting in a sine wave and it's going through. And then for every single point in that sine wave, we measure a whole spectrum out. So here we've kind of binned it in different bins rather than showing the frequency. And so here we've got about 350 points out for every single point we put in. And one of the reasons that's so attractive is that the set of properties that we want are the sort of non-linearity. So just like a non-linear response to an input, we need the dimensionality to increase. And what that means is basically do you get like more numbers out than you put in? So we put a one-dimensional input in, and we got a 350-dimensional vector, if you like, output coming out the other side. And also we need the kind of memory which fades but is strong to start with. And essentially the nanomagnets, you get all these properties for free in the physics. You actually couldn't stop it doing it if you wanted to. Okay, and so one last thing to say is the computing we're doing is a bit different to what I've talked about before. It's called reservoir computing. So here's, we scale our inputs. Here we do the kind of field loop training. Here we measure our outputs, and then we do a one-step learning on a conventional computer. It's called linear regression. So there's none of the going round and round in circles like in a neural network, but we are doing some conventional computing, which makes it much more easy to at least define your problem and get an answer. And so essentially, so we do that for a while in our training data. And during the training, you're allowed to update what we call the weights. Like, this is our set of outputs, and for each one, you can multiply that by any number to generate your final target output. But then once you've done the training, you say, okay, you're not allowed to change those weights anymore. So now we have no degrees of freedom at all. And we just continue doing the measurement, and we see if it's still good. Okay, so what we're going to do now is we're going to predict the hormone levels in the blood, or otherwise a chaotic equation, which is called the Mackey-Glass equation, which describes that. And so here we have, you can see the black line is always 10 points ahead of the red line. So basically we're predicting 10 steps in the future all the time, with no degrees of freedom beyond what we've done in the training. And you can see that it keeps working really pretty well, even though this is a very hard computing task. Okay, so basically that was pretty good, but we thought maybe we could do a bit better. So what we've done here, and again, this was really driven by Killian Sterning and Jack Gartside in collaboration with computer scientists in Sheffield. And so here we've made like a 3x3 virtual neural network of our reservoirs. So here it's a very small neural network, but each neuron in the network is very complex. And so essentially what we do here, so we put our inputs separately into each of these three arrays. Then we have to take our output, identify what we think is important from it, and turn it back into a one-dimensional thing. And then rather than putting our input into the second layer, we're going to put our scaled output back in again. And so then we're going to do the same thing again and again. And so we've made a 3x3 network. And when we do that, we saw a really quite dramatic improvement in the performance for lots of different tasks, but I'll show you the same one again. So the top is our best single reservoir, and you can see it's doing pretty well, but there are some issues. Whereas down here, this is the kind of physical neural network, and you can see really dramatically better performance. Right, okay, so the last thing, having said all that, it took us a long time, and it took us a long time because our input scheme with magnetic field is very slow. So what might we be able to do better? And so the first thing, which was really the topic of the PhD with Holly Holder, and it's a collaboration with Rupert Alton's group, is we started shining lasers at our magnets to see if we could reverse it. And somewhat to our surprise, we found almost immediately that we really could. And so here we're scanning the laser across our magnets, and if we do that, we see that in the MFM that the thing is reversed. And if we go back and do it again, it reverses back. And we're not using any magnetic field at all, this is just the laser. And there's part of that we understand really, really well, and that's the nanophotonics, if you like. So essentially, because the wavelength of the light is really close to the feature size, both in the plane, and that gives us what we call a plasmonic antenna, but also the feature size of this kind of spacer layer we've got underneath. This gives us what we call an interference effect. So basically, if you have half a wavelength from where the light comes in to where the light goes out, then you get destructive interference with like the next photons coming in. And so essentially, that stops any light escaping the structure at all. And if we put those two things together, we can get more than 80% of the absorption of the light within the nanomagnets themselves. Whereas for reference, if we just put our nanomagnets straight on top of silicon, we would get about 2% absorption. Okay, so it really changes how the physics works. Okay, this is quite complicated, but really the thing I want to show you is now when we try and do it in dense artificial spin isotype arrays. So here we've scanned down a row here, and you see all these dark dots here. Well, so these are our good old artificial spin-ice vertex types, and the one with many dark dots is a 3-in-1 out state, so it's a very high energy defect state. And so the obvious first thought is that all we're doing is we're making the thing hot and it's randomizing and then it's cooling down again. But if you did that, the last thing you'd expect is to get a whole bunch of high energy defects in a row. It would go to one of the low energy states. And so, and you can see here, we can write whole long lines, and basically something happens in all of them. Okay, so it's very low power. It's very interesting physics. It's still a bit slow and clunky because we're writing one thing at a time. So we moved on from there, and we started exploring, along with the group of Riccardo Sapienza, and also Jack and Killian, who are leveling up with every slide, and now both have their own research activities, have different ideas in this direction. But anyway, so what a DMD is basically a stripped down version of the kind of projector that we're projecting these images with. And it's basically an array of different digital mirrors. And you can turn each one on and off. So if we illuminate with a laser beam the DMD, then we can basically write any pattern that we want in the thing and directly project images on our samples. So here we've just projected a checkerboard with a pitch of like 1 or 2 microns in the square, okay? And underneath you can vaguely see our nanomagnetic array. It's hard on the scale. Yeah, also this is a paper we've done, which is the PhD work of Kit and Jakob and Anna, really looking at kind of machine learning in a very different system which doesn't have magnets in it at all, but it's really quite powerful. And that's on the archive preprint server if you want to have a look. Right, okay, so anyway, so here's our network. Here's the structure, here's the MFM image. We've put a big field on and saturated everything in one direction. And in fact, we're going to have 3 samples where we've done the same thing in all of them. And what we're going to do now is we're going to project some pictures with the laser on there. And when we do that, you can see that everywhere we projected with the DMD, simultaneously in one 400 picosecond shot, we've done something in all of them. And the next thing says, if you look at all these like very bright and very dark blobs, again, this is not like the kind of low energy spinized structure. We've got some very high energy defects going on here. And then because around here, the magnetization of one magnet kind of props up the others, it's going to be much harder to reverse all the bars with field out here than it would be in the middle here. So basically we've defined a region, now a field window, if you like, where we can do computing in this area here, which we've just written, but we wouldn't do anything in the areas we haven't written. So that's all very nice. Okay, one last thing. So how are we going to make it more efficient? What's our outlook and future plans? So really, this is a defining challenge for our times. AI is not going to go away. There's only going to be more and more AI. And the current model of just building bigger and bigger models and brute forcing the answer, while it works incredibly well, is just not sustainable. So we need to do something different. But there's no point doing anything different unless people adopt it, right? So you actually have to get people to use it. And NVIDIA has become, almost overnight, $1 trillion company because it totally dominates AI hardware. And it does that because it's incredibly good at what it does. And they've got a lot of very smart people. So it's not that they're stupid, but it's like they're providing what their customers want right now. But anyway, if we want to do something, we need a credible alternative. And that's a huge tech challenge. And that is going to need expertise from all disciplines. And it's going to need investment at scale. But in one sense, that's lucky, because Imperial's strategy, which I commend to you all, Science for Humanity, has a real focus on what we call convergent science. And so essentially, we're going to build some schools of convergent science. And what that really means is still being discussed, but it says on the website, something I'm safe to say, it's going to create deeply integrated research and innovation communities and deliver societal impact. And one of them is in human and artificial intelligence. And they've made me one of the co-directors, so I think it's clear that they're kind of okay with us trying to do this sort of problem at scale in this thing. And so I should say there's many, many kind of wacky computing schemes similar to ours, which you might call neuromorphic computing. But all of them, they're going to need nanofabrication at scale. They're going to need knowledge from neuroscience. They're going to need quality machine learning algorithms, which are specifically developed for their thing. You know, you need the computer science, you need the materials. And so basically, what this definitely will be is some sort of convening point where we can bring all the partners together to develop strategic approaches to trying to tackle this enormous problem. So one thing that's encouraging is we don't have to start from scratch and do it all in one go. So there are already things you might have heard of called like AI accelerators or neural processing units or tensor processing units. And in fact, NVIDIA shot to prominence by making what's called GPUs, or graphical processing units. So original computers didn't have these. This is a kind of bolt-on thing when we started using like computers to do really heavy-duty image processing. And essentially, there's already ideas to do the same thing, but with even more dedicated machine learning chips. So I think over time, we'll see, you know, the giant cloud and the huge scale NVIDIA chips are not going to go away. But there are more and more tasks where we won't need to do that, where we'll be able to train locally chips to do the thing without this huge energy cost. So that's one dream. The other dream is just to do machine learning on the current hardware in a much more efficient way. Now, you may have seen there's been a lot of stuff about DeepSeek in the news recently, because they were able to train at a much lower cost this machine learning model. And if asked why their thing works so well, they would say they have an emergent behavior network. And so what that means to them is that complex reasoning patterns can develop naturally without explicit programming. And I could have told them that, and hopefully now you've seen this talk, so could you. Anyway, and so finally the most important slide, huge thank yous to my current and former PhD students. I wasn't able to highlight everyone's work, but great thanks to you. Dear friends in physics and the rest of Imperial, some external collaborators highlighted over here, and lastly my funders. Thank you all for listening. Cheers.
Thank you very much for this inspiring and interesting talk and lecture. Now we have time for a few questions from the audience. How fast are your brains working?
Oh, my brain's completely stopped. Believe me. It was very interesting. Thank you very much for the talk. My question is, I suppose, simple because I'm not a physicist. What would be the main roadblock, do you think, of your research going forward? Would it be funding from large research agencies, or maybe you need an assistant researcher?
Well, I mean, there's lots, and I tried to outline them at the end when I talked about the Convergent School. Like, it's not a question of going with one research grant from what we're doing now to, you know, a real product. So you may have seen some of these AI accelerator companies. There are startups, things like Light Matter. Light Matter has received $800 million in venture capital over 5 rounds, and it doesn't have a product for sale yet. Okay, you know, it's a serious problem, okay? This isn't like, you know, NVIDIA is hard to beat. There's lots of the big tech companies want a piece of the action, and, you know, they can't do it. So you've got to do something that's really good. Now, if you just want to make a little smart sensor, you train for one thing. It might not be like that at all. A little startup might be able to do something there. But if you really want to replace what's going on in the cloud, it's a colossal problem across the whole stack of STEM. And also it needs investment, it needs a favorable policy environment. You know, really, everything has to come together. That's why the convergent science is so important.
Thank you very much.
Any more questions? Rupert, yeah? This is the online question, I see.
Yeah, I have an online question here. If you are going to submit an online question, please do put your name and affiliation. This is anonymous, but I thought it a useful one. Do you think quantum computers will eventually be useful for AI?
Also an excellent question. So obviously quantum computing is also a massive area and somewhat different. It looks really promising. One of the big challenges quantum computing has at the moment is actually the fault tolerance, getting enough qubits together and having the fault tolerance right. Now, one of the great things about kind of machine learning or neuromorphic computing is it has a sort of fuzzy logic element to it. So it basically has fault tolerance built in. So I definitely think there's real attraction going forward in trying to marry the best of quantum computing with the best of neuromorphic computing.
Any further questions? Yeah, please.
Thank you. How much of the future energy requirement could be covered by nuclear fusion if we ever get it to work?
Well, I mean, on some level, it's limitless, right? So all of it.
I mean, with everything, there's a resource limitation at the end, even with neuromorphic computing or anything we do. So what would be, rephrasing this slightly, what would be the resource limitation for computing solutions like this? There will be one, yeah? I mean,
yeah, of course. I mean, well, I mean, you have to get everything together. So it's almost certainly funding. And the scale.
But it could be also in terms of certain materials, for example, that are.
Of course. So
I don't mean resource now in the sense of funding, but in the what is.
Okay. So
it's a bit of a question like with the cars. Yeah, we move away from oil, but now rare earths become a problem.
Okay. So one thing to say is that our brains are totally amazing. So the connectivity is in 3D. And as we learn, the physical structure actually changes. And, that is obviously incredibly powerful. So the more we can get to a physical structure that we can make on large-scale devices, but captures that element, the better. But that's an enormous challenge. I don't know how to do that.
We can build organic computers. Another online question?
Yeah, I'll ask another online question. Anonymous again. Current computers are general computing machines capable of many tasks. Will neuromorphic computers be the same, or will the training specialize them?
So at the moment, essentially all AI that we have, and that's certainly true of the early neuromorphic computers, will be specialized to a specific task. The AI is getting more and more towards a general intelligence, and essentially that is why we use the very inefficient thing at the moment, is because it's a general computing scheme, so you can run whatever you want on it, which is obviously much more convenient. But now we're doing AI at such colossal scale. It's just a different game, and so I believe we're going to have to get more and more specialists to specific things. At least many of the tasks that we do on AI, it doesn't really need a computer in the cloud and this huge stuff. It just needs a little bit of training, which we're not able to do at the moment locally.
There's another question up there.
Thank you for the talk. My question is a bit broader and not quite about physics. How do you think is artificial intelligence and access to artificial intelligence affect society? Will it be equalizing, or will it be stratifying?
It's an excellent question. It depends how it is implemented. The more we go towards this thing where training the model is more and more expensive, and so access also becomes more and more expensive, then you feel like almost the more unfair our society might become, where some people have access to this amazing tool and some people don't. So one of the great things about trying to make it more efficient is it makes it more equitable as well, and we can try and keep access for all. Does that make sense?
Yeah, right back there.
So thank you for an inspiring talk. I come here as a computer scientist, and we're in the business of trying to abstract away from the hardware that you've been describing. Can you tell us what we should be simulating or assuming about what the kind of hardware that you haven't built yet might do in order to be able to understand the neural architectures, for example, that we should be hoping to run on this kind of hardware?
Oh, that's a great question, and I really wish I knew the answer. So there is a whole field which is emerging in terms of how you do the next generation of physical neural networks beyond what I showed today, where you really do training in the physics. And to do that, you have to have an algorithm which is specifically designed for your physics. Because the backpropagation through time thing, which is used in essentially everything at the moment, basically requires time reversal symmetry, and almost none of the materials which look good for this sort of stuff have that. So you just can't do that. You have to do something that's different. And so what we really, really need is hardcore machine learning people who start working instead of just on backpropagation, but on stuff which is either really inspired by how the brain works, which is called neuro-AI a lot, or for specific physical systems, which are often called physical neural networks. So I would say that's where we want to go and need to go.
Thank you. You should come and visit us.
I'd love to. Rupert?
I have a question from Cesar Freitas, a PhD student at Imperial. What are the space requirements of these nanomagnetic grids, and how scalable are they? For example, would multi-billion chips of these systems be feasible?
Excellent question. So at the moment, because of the way we've done a lot of the experiments, we actually need a lot of nanomagnets. But that is essentially only to get the signal to noise in our experiment up. So in that case, the thing is quite big and it isn't very scalable. But in principle, you can do something with much, much smaller microwave pickups, much, much more densely packed. So, I mean, if you look at how big the current computing infrastructure is, it's like, you know, you might be able to do a lot in one NVIDIA box, but it's kicking out so much heat that you can't have anything around it for meters cubed in space. So you have got, you know, opportunity to be competitive in terms of the size, because we're doing so much more with one computing element than is being done in the conventional ML.
I think there was a final question, perhaps somewhere in the middle.
Thank you. So this might be a silly question, but what is neuromorphic computing?
There are no silly questions. Sorry, maybe I didn't explain that very well. So neuromorphic just means brain-shaped. And so on some level or other, the idea is that it's inspired directly by the architecture of the brain. Now, you know, there's a version of that which really is inspired by the kind of the soft chemistry 3D structures within the brain. What we're doing is not really like that. It's actually kind of directly inspired by the fact that the algorithms for current machine learning came from magnets, and we're trying to go back to the start with the magnets. So we're trying to make hardware which is specifically designed for machine learning rather than specifically looks like the brain. If that makes sense.
Thank you very much. I'll remember that tomorrow morning when I put the kettle on, this corresponds to 7 Google searches. Thanks for this really inspirational talk. And now we'll have the vote of thanks from Steve Bremmel from UCL. Thank you.
I think I'm mic'd up. Yes, I am. Yes. So good evening, everybody. As I've been introduced, I'm Steve Bremmel from UCL. I'm the UCL director of the London Centre for Nanotechnology, which is a collaboration between Imperial, UCL, and King's College. So it's my privilege and my honour tonight to thank Will, wherever he's gone, there he is, and also to thank all the staff here at Imperial for putting on this fantastic lecture. But I'd like to say a few words and hopefully put the lecture into context. I'm in a fairly good position to do that because I've had the pleasure of observing Will's scientific trajectory over something like a quarter of a century or more. With this personal knowledge, I didn't have to go to ChatGPT tonight to write these few words. This is all my own stuff. About something like a quarter of a century ago, I forget exactly how long, Will did his PhD at the Royal Institution and also at UCL, and I was, I think, his UCL supervisor in that program. And at the time, there were several groups in the area who were interested in magnetic materials, and there was a lot of work done, there were lots of discoveries made, a lot of ideas developed, and most importantly, everybody had a lot of fun, which is probably the most important thing of all in science, I think. Now, at that time, I and several others had what might be called a very curious fixation on exotic magnets. Right, now these magnets that we thought were exotic had a strange thing about them. It would be very hard to explain to the general public why we were so excited, because they basically didn't have any properties of any use, right? They didn't even stick to the fridge. So if you take, just put in context, we also talked about spin glasses. They don't stick to the fridge at all. Spin ice might stick to the fridge, but not for very long. But generally, these things are fairly sort of passive in their properties. Will's often reminded me since that at that time, he and I once had a conversation. He'd been doing his PhD for some time. And the conversation went down the lines of, so what uses are there for all of these things? And I suddenly realized that we, the supervisors, had been rumbled, and Will had realized that there was no use to all of this stuff. It was all just academic. And at that moment, I think that was a slight sort of Damascene moment for Will, that he suddenly realized that he was going to go on and make them useful. But I remember remarking rather cynically that actually maybe there was one use, and this guy John Hopfield had made a link between magnets, between spin glasses and neural networks, which could be useful in machine learning. And you could see a look of determination come over Will at that point. He was going to take that forward. And so in order to do useful things, he, of course, came to Imperial, which is where everyone does useful things. And he started working with Leslie Cohen, and you learned a lot of new things, and did some fantastic work. So as he's already mentioned, sort of 10 or 15 years ago, it was very fashionable to talk about magnetic monopoles in spin ice, and Will and his collaborators made some really fantastic contributions to that, some very important contributions, showing how they could make analogues of magnetic monopoles in spin ice in micromagnetic arrays, and track these and image these things. And then that sort of went on to subsequently develop some new aspects of science, and Will went on to build an absolutely fantastic group of students and postdocs here at Imperial, but also collaborators, including collaborators in the London Centre for Nanotechnology back at UCL, and collaborators elsewhere. And we've seen some of the fantastic work that they've managed to do in sort of developing magnetic systems that are useful for neuromorphic computing and related subjects, types of computing that can happen at very low energy, like the human brain. Magnets are well suited to this because it's fundamentally a rather low energy phenomenon. So I think on behalf of everybody here, then I'd like to finally thank Will for the lecture, and all the organisers who've made it work so well. I think we've been really inspired by the vision you presented, Will, and there's some hope for the world with the sort of neuromorphic computing and all the work you're doing. And we'd like to wish you the best for your future research and your future career at Imperial College and beyond. So thank you.
Okay, this concludes the proceedings, and I think there are drinks outside where we can all celebrate now. Thank you.